Good morning. Hi, everyone. 안녕하세요. Hi. So we are talking about approximation algorithms. We have seen an approximation algorithm, namely one for the metric traveling salesperson problem, an algorithm which had approximation ratio 2, which is what distinguishes an algorithm from a heuristic, approximation heuristic. We've been able to guarantee that Christofides' algorithm it runs in polynomial time, which is not possible probably for exact solutions, exact algorithms. But the benefit of running in polynomial time is kind of traded for a non-optimal solution. On the other hand, the solution returned by Christofides' algorithm is no more worse than the optimal solution up to a factor of 2. So this is approximation ratio for minimization problems. The traveling salesperson problem is a minimization problem. We're looking for the shortest, for the cheapest tour. And Christofides' algorithm exceeds, or the tour returned by Christofides' algorithm is always a tour, but it may exceed the optimal tour by a factor of 2, a factor which of course is larger than 1. For minimization problems, so the approximation ratio is a factor larger than 1. For maximization problems, the approximation ratio is a factor smaller than 1. Right? So for maximization problems, the exact algorithm is supposed to give the true optimum, the true maximum, which in general may take exponential time to find. And an approximation algorithm is supposed to do the same in polynomial time, but return a solution which is slightly less than the maximum, the exact maximum, less by a factor of 1 minus epsilon, that is by a factor which is smaller than 1. So that approximation algorithms for optimization problem come in these two categories: approximation algorithm for minimization problems with ratio greater 1, and approximation algorithms for maximization problems with ratio less than 1. And we're currently discussing an approximation scheme. An approximation scheme is basically a family of approximation algorithms where you can tell the algorithm how good an approximation ratio you want. So Christofides' algorithm has this hard-coded approximation ratio of 2, and it's actually area of research how to find what is the smallest approximation ratio that can be achieved in polynomial time for the metric traveling salesperson problem. For the knapsack problem, arbitrary approximation ratios arbitrarily close to 1 can be achieved. And actually they can be achieved by one single algorithm that receives the approximation ratio as input. And we're currently discussing this algorithm. So to remind you, a knapsack problem can be considered as a decision problem where we're given bounds on both the values and the weights. Lower bound for the value must be at least this and that. And upper bounds for the weight must be at most this and that. And the decision problem answers whether these combined constraints are feasible or not, whether there exists a subset of the packets that achieves that both bounds. Then a knapsack problem can be considered as a maximization problem where the weights are considered as constrained, as hard constraints. They cannot be exceeded. And the goal is to maximize the values to choose packets that have the largest possible total sum of values subject to that weight constraint. Maximization problem, or it can be considered as a minimization problem, where now the values are considered as hard constraints. You must not uh, you must return values at least capital V. How small can you make the weight in order to attain that value? Minimization problem. So for minimization problem, approximation ratio is larger than 1. For maximization problems, approximation ratio is less than 1. And we're going to take a view of the knapsack problem as a maximization problem. So we're going to expect an approximation ratio less than 1. But during the course of our algorithm, we're actually also going to consider it as a minimization problem. Namely, the algorithm we have been discussing is an exact algorithm. So we cannot expect polynomial time for that exact algorithm. But that algorithm is actually a dynamic programming paradigm algorithm, which is of interest of its own. And also this algorithm is the key to later the approximation algorithm. Namely, this algorithm will turn out to run in strongly polynomial time, which means in time polynomial in n, the size of the input, the number of packets, plus v, where v is now the value of total value of the packets, or put differently, the value that we're looking for subject to the weight constraints, that is the answer to the maximization problem. So let us recall that the dynamic programming algorithm proceeds to fill this table, where in each entry, each row, the rows are indexed by the value constraint. We must choose packets that the total value must be at least V. So here we consider kind of a minimization problem as part of our goal to solve the maximization problem. We consider a family of minimization problems with a value known as lower bound constraint. And there's a second parameter, namely to consider only the first M packets, not all packets right from the start. And this allows us to kind of gradually fill the table by gradually taking into account more and more packets, by gradually increasing M, by proceeding from the first column gradually to the next, until the mth column. And this is what the quantity that we're actually interested in when we take into account all packets in our minimization problem. Among all packets, what is the least weight that is feasible in order to satisfy the value bound given here? And we've derived equalities for the different entries in the table. We've seen that the top row can be initialized very easily with zeros. We've seen that the leftmost column can also be initialized easily. And we've seen how to proceed from left column to the next column, from this column to the next column, using this equation number Roman 5, which basically says that once we have found out all the possible values that are feasible, and for each feasible value, what is the optimal weight among the first M packets. Now, if we take into account the M plus first packet, there are two cases. Either this first M plus first packet is part of the optimal solution, or it's not. If it's not, then we can just copy the entry from the previous column, because if it's not, then we can simply discard it, and we're back in the case where we've only considered the uh, previous packets. Whereas if it is, then we can play a kind of variant of the knapsack problem where we remove the new packet. Thus, we have reduced the feasible value, and we remove the packet, which also means we have removed its weight. And then we obtain an optimal solution to another instance of the knapsack problem, namely one where the goal is to minimize the weight minus the weight of the packet we have just removed, and to achieve the value bound minus the value of the packet we have just removed, and consider only among the packets number 1 to m minus 1, discarding, ignoring the packet m we have just removed. And which either one of the two quantitative gives the smaller weight, this is going to be our solution, our minimal weight, when taking into account the next packet number m as well. So this justifies this equation, and mathematically and computationally, this equation allows us to fill the table column by column from left to right. And since each row can be filled, or each cell, each entry can be filled in polynomial time using that recursion. And since the number of columns is polynomial in n, it is actually equal to n. The running time of the algorithm is dominated by the number of rows in this, to fill the number of rows in this matrix. And we fill the matrix until the row number v, capital V, where this is the quantity we're actually looking for. Namely, we're looking for the the value that is just barely feasible, subject to the weight constraint. So whenever the minimum weight is less or equal to our constraint weight, then that value is feasible. When the minimum weight exceeds our weight constraint, that next larger value, v plus 1, is not feasible anymore. So we're looking in the rightmost column for the first entry that just barely satisfies the weight constraint, and the row index, the column index v, that's actually the optimal value we're looking for. And so the running time is therefore polynomial in n plus capital V. Capital V, the quantity we're looking for, polynomial in its value, not in its binary length. And that's what makes this algorithm not a polynomial time algorithm. We cannot hope for polynomial time algorithm, since the knapsack problem exactly is NP complete. So when this value, the value we're looking for, is kind of large, exponential in the inputs length, the binary length, then this algorithm will be not a polynomial time algorithm. Whereas if this value is small, then this is can kind of become a polynomial time algorithm. And we've also already discussed a kind of a trick how to make that value small. Namely, if it happens to be large, then we can kind of scale down the problem. So for instance, if all the values, observe that the weights don't enter into the runtime. So we're going to ignore kind of the dependence on the weights, whether the weights are large or small. Independence on n doesn't really matter, but the values, right? And our trick, our observation is, if the values are given like in, let's say, American US cent or Euro cent or in Korean won, then the values are likely going to be very large numbers as integers, right? But when instead proceeding to dollars instead of cents, to euros instead of cents, to John won or to Man won, then the values suddenly apparently become small. but they may become fractions, right? So if something would cost like uh, uh, 2,301, then expressing this in multiples of John 1, that will be 2.3, which is not an integer, right? But problem specification and our dynamic programming algorithm heavily relies on the values to be integers. Otherwise, we cannot inductively proceed from row to row, right? So the row numbers are really the values. We cannot proceed with fractional values. So what we can do is we can round to multiples of John 1, right? But this rounding, of course, changes in the end the outcome of the algorithm. And on the next slide, we want to analyze the effect of this rounding. And let's first do that informally. So let's say our values are given in Korean 1. And now we round the values to multiples of man 1. We're going to round the values. What are we going to round them? Let's round them downwards. Okay. Rounding downwards to the next smaller multiple of 1, 1. Then the solution returned by the algorithm will be a feasible solution. It satisfies the weight constraint. We haven't affected the weights at all, but the values returned by the algorithm could be different, right? Because now the algorithm operates on values we have modified, right? How much different will they be? Well, there will be, in general, there will be, right, how much have we affected the value? We've affected the value of each item by at most man 1, right? By rounding the value of an item to the nearest multiple of man 1. That means we change the value by at most 1 man 1. Okay. Now, if we have n packets, that means that the overall solution returned by the algorithm will differ from the original unrounded solution by at most n times man 1. Okay, and this is exactly what we want, what we see on the next slide on a more rigorous mathematical perspective. Please ignore the lemma for now. This is correct. This is a mathematical justification, but I think pedagogically it's much more easy to understand this with the argument I've just told you, the rounding argument. Namely, we round the values of the packets. We round them down to multiples of k here. So in our example with man 1, k would be like 10,000. So we divide every value by 10,000 and then round down. And later we're going to multiply by 10,000 and the result will be rounded to the next multiple of 10,000, right? And so by dividing this is what accelerates the algorithm, right? So now the running time of the algorithm is not n plus capital V, but it's n plus capital V divided by k, because we've divided all values, packet values by k. Okay. So that now the running time of the algorithm is n plus v divided by k, where k is a natural number that we're going to choose later. That's a parameter that we're going to choose. This is like we're free to round the values of the packets to multiples of John 1 or to multiples of man 1 or to multiples of Shipman 1. That's kind of our choice. Choosing k larger makes the algorithm faster, but intuitively also makes the solution differ more from the exact solution, because rounding to multiples of OG1, of course, has a heavy effect on the solution returned if your presence particularly if your presence don't exceed odd 1, then everything will get rounded down to 0, right? So here we have a trade-off, a parameter k. Increasing k makes the algorithm faster, but also less accurate. And our goal is to analyze the accuracy and then to choose k large enough so that on the one hand, the algorithm will have running time that becomes polynomial, and on the other hand, not too large so that the error will still be sufficiently small, namely so that we achieve this approximation ratio of 1 minus epsilon, right? Minus epsilon, number less than 1, because we're talking about a maximization problem, and epsilon is going to be the parameter input to our algorithm. So let's see how much rounding the packet values. Uh, so, okay, let me be more specific. So we divide the packet values by k, which in general will not be an integer. Then we truncate that, thus obtaining an integer. Then run the algorithm. And at the end of the algorithm, we're going to multiply the results produced by the algorithm by k again. And this is basically the rounding, right? First divide, then truncate, and then multiply by k. This means rounding to the next multiple of k. And what we basically have observed is that every single value of a packet will this be affected by at most k. So in our example, by at most man1 absolutely. And since we have at most k, we have precisely, since we have n packets, that means that the overall value returned by the algorithm after the rounding will differ from the exact value by at most n times k, n times man1 in our example. Does that make sense? So every single packet value gets affected, gets changed by at most k when rounding to the next multiple of k. And the total value of n packets will therefore get affected at most by n times k, so that the value returned by the algorithm will differ from the exact value v, which we don't know. The value returned is denoted here by v prime, will be no larger than v. It could be less than v, but it will be no less than v minus n times k, because we have affected the total value of all packets by no more than n times k. And now we reformulate that as v times 1 minus something, and this 1 minus something is going to be our epsilon, right? So we want to achieve approximation ratio 1 minus epsilon, which means that the solution we return should have value at least the optimal solution v times 1 minus epsilon, and 1 minus epsilon is the approximation ratio. And unlike with Christophidis' algorithm, which has a fixed approximation ratio, here the approximation ratio is kind of given by the user. The user says, I want approximation ratio 1 minus epsilon. This is the value of epsilon. Here you go, algorithm, deal with it. So how can the algorithm deal with it? How can the algorithm make this expression less than epsilon, right? That's the goal. This expression should become less than epsilon, and this is let's see, no, it should become larger than epsilon, right? It should become larger than epsilon, and this can be achieved by making k sufficiently large. And now the analysis says that if we could choose k roughly k, where is it here? If we choose k like this, then it will be sufficient. No, my bad. We should choose k small enough. So if we choose k equals to 1, then we get the exact result, right? Choosing k equal 1 means we round to the next multiple of k, and the next multiple of 1, that's not rounding at all, right? So when k is equal to 1, this scaling will not affect the values at all and thus return the exact solution, but at exponential cost because this is the value. On the other hand, making k large will reduce the running time, right? But it will affect the error. And we have this kind of narrow range to choose k such that the error should be smaller than epsilon, but k should be large enough for this to become polynomial. And the value of k to be chosen is, or one value is this. So let's look at this. It depends on epsilon, of course, right? So the smaller epsilon, the more accurate we have to calculate. That means the smaller k must be chosen. And here's the quantity which we can compute. Namely, right, so we want this here, this quantity to be less than epsilon. But to this end, we want to choose k. But the problem is that we don't know capital V, right? Capital V is exactly what the algorithm is supposed to calculate. So the algorithm must choose k sufficiently small and sufficiently large for this to be less than epsilon without knowing capital V. Cannot calculate capital V exactly because that's exactly the purpose of the algorithm, to do that approximately. On the other hand, we have these bounds on capital V. Observe this bounds says capital V is the optimal solution, the optimal value. That's at most the total value of all packets, right? So when summing all values of all packets, that will exceed V, right? That will dominate the optimal value. The optimal value is less than the value of putting all possible packets into the knapsack. On the other hand, the total value of all packets combined is at most n times the optimal value, because the optimal value is at least the maximum of the largest value packet, right? So remember that we've already excluded all packets whose single weight does not fit into the knapsack. Therefore, all the remaining packets, single packet can fit into the knapsack, and we're taking the maximum value. Therefore, if we consider the maximum value of all packets, that the optimal solution will be at least at large, and so therefore n times the optimal solution will be larger than the total value of all packets combined. So we have a kind of know that the range of capital V, which you don't know exactly, is somewhere between this quantity, which we can calculate, and this quantity divided by n, right? So if we solve this inequality for V, that means this sum divided by n. And so by choosing k equal to this, therefore this means that this will be less than epsilon times V, right, divided by n. So one n here is in the division, and the rest is, because of this inequality, the total sum of all packet values divided by n is less or equal to V. So, and because of this inequality, if we plug this in, that means that n times k divided by V is at most, well, the V cancelled, it's at most, and the n cancel is at most epsilon. This quantity is at most epsilon for this choice of k, and this choice of k can be computed in polynomial time. And this is what the algorithm will do. Finally, choose the parameter k computably, and thus indeed obtain and guarantee this approximation ratio. So let me say it again and put differently. So the algorithm receives as input the integer packet weights and the integer packet values and epsilon. epsilon specifying the approximation ratio 1 minus epsilon. And then based on epsilon, the algorithm calculates this value of k. This sum can be computed, divided by n squared, multiplied by epsilon, and then round it down in order to make an integer, and then round all packet values to the integer multiples of k, that k just that's computed, and then run the strongly polynomial time algorithm, the dynamic programming algorithm from the previous slide. And by this inequality, the solution thus returned for the rounded packet values will be an approximation to the exact solution up to error 1 minus epsilon at most. And the running time of this algorithm is now polynomial in n. Why is that so? Because if we divide capital V by k, and k, that's important here. This is important. V divided by k is at most n squared divided by epsilon plus 1. That follows from the first inequality, right? So k is chosen like this. That means the sum here, k, is roughly the sum of the packet values divided by n. And we know that the optimal solution V is less or equal to this sum. Therefore, V divided by k is less or equal to n squared divided by epsilon. So this part of the inequality enters here, and this part of the inequality enters here. And together, this means that V divided by k is now something polynomial in n, basically n squared, divided by epsilon, so that the running time, total running time, will be polynomial in n and polynomial in 1 over epsilon. So that means that the smaller epsilon gets, the better approximation ratio we get, the closer we want the approximations to be to 1, the larger the running time, right? So if epsilon is, let's say, 1%, if we want an approximation up to 99%, then that means that the running time is now 1% divided means 100 n squared. And if epsilon is even smaller, if epsilon is 1 per mil, 1 over 1000, giving a better approximation ratio, then also the running time increases to 1000 times n squared. So here we can kind of very nicely see the trade-off of this algorithm between the quality, between the approximation ratio. The smaller epsilon, the better the approximation quality, the closer the ratio to 1, but also the larger the running time. The good thing about this algorithm is that the running time will increase only with 1 over epsilon as a linear factor. Other approximation algorithms for other problems may have 1 over epsilon in the exponent, so that the degree of the polynomial actually explodes with epsilon. Algorithms of this form are called fully polynomial time approximation scheme, FPTAS, fully polynomial time approximation scheme. And fully polynomial means exactly this, that the parameter epsilon governs the quality of the approximation, enters polynomially, does not enter in the exponent. Okay, so to summarize, the algorithm we've just discussed has the following property, which is called fully polynomial time approximation scheme. For every given epsilon, parameterizing the approximation ratio, the algorithm achieves an approximation to the knapsack maximization problem up to error 1 minus epsilon as a factor in time, which is polynomial in n, and polynomial in 1 over epsilon, where since epsilon is small, 1 over epsilon could be large. And algorithms that have this property are called FPTAS, polynomial time approximation schemes, algorithms where the running time depends polynomially on n, the length, and on 1 over epsilon, as opposed to 1 over epsilon being, for instance, in the exponent. And the algorithm, to summarize, the algorithm first calculates the appropriate choice of k, the kind of rounding parameter, then performs the rounding, then executes the exact dynamic programming approach from the previous slide, and then scales the values back, multiplies everything back with k, and our analysis shows that this indeed A is polynomial time, algorithm running time polynomial in n plus 1 over epsilon, and secondly, it achieves this required approximation ratio. So this concludes our discussion of approximation schemes for the Knapsack algorithm, an entire family of approximation algorithms. And now we proceed to limits of approximation. Maybe some problems, some maximization or minimization problems provably cannot even be solved approximately in polynomial time. Well, unless p equals np, of course, unless the minimum problem has a positive answer, but few people believe that to be the case. So that we have a very rich and nice structure here. Some problems can be solved exactly in polynomial time. Other problems provably cannot be solved unless p equals np, among them traveling salesperson and knapsack problem. But among them that cannot be solved exactly in polynomial time, some can be approximated by a constant factor, like the metric traveling salesperson problem. Some can be approximated arbitrarily well, parameterized by epsilon, such as the knapsack problem, and some cannot be approximated at all. And here we want to see such an example of a problem which cannot be approximated at all. Namely, we're going to show that the general traveling salesperson problem, namely the one without the hypothesis of the edge weights to satisfy the triangle inequality, that is not the metric traveling salesperson problem, this can be approximated. It cannot be approximated up to any constant, actually. Well, it can be approximated up to, let's say, n, but that's kind of trivial. We just take any tour. That will not be a good approximation. But it cannot be approximated up to any constant unless p is equal to np. And now here's the proof. That's an interesting thing to prove, that something cannot be approximated. It's a proof by contradiction. We suppose that the algorithm A does approximate the general, the non-metric traveling salesperson problem up to some constant factor c. So that's kind of 1 plus epsilon with very large epsilon. Actually, any fixed natural number is epsilon. And then we're going to convert that algorithm A into an algorithm B that solves the Hamiltonian circuit problem. And as you recall, this is a decision problem. So here there's no approximation involved anymore. Hamiltonian circuit problem asks, is there a Hamiltonian circuit in the graph, yes or no? And if we can answer that in polynomial time, then since this is an NP-complete problem, this means that P is equal to NP, contradicting our hypothesis. So how can we convert this hypothetical algorithm A that approximates non-metric traveling salesperson problem up to factor C? How can we convert that into an algorithm that solves the decision problem, Hamiltonian circuit problem, exactly? The algorithm B will receive as input a graph, an instance of the Hamiltonian circuit problem with n vertices, and it will turn that graph into a graph with edge weights. right? So the input graph in general may have not all edges present, otherwise Hamiltonian circuit problem is trivial, has the answer yes. So some edges may be absent, and now what our algorithm B will do, it will artificially assign weights, natural number weights to the edges, namely a cheap edge with little weight 1 will be the one that has is an edge that is already present in the given input graph. So this will be given, these edges that are present in the graph will be given small weight. And whenever there's an edge absent, an edge from U to V, let's say, then we're still going to include that edge. We're artificially adding that edge, but we're going to make it very expensive. We're going to charge, we're going to create the weight for that edge to be n times c, where c is that constant, that hypothetical approximation factor, and n is the number of vertices. And let me emphasize that again. Our algorithm B will modify the input graph. It will turn this graph into a complete graph, for which maybe the Hamiltonian cycle problem is trivial, but it will make the edges that are not present originally become very expensive, so that in the end, when our hypothetical approximation algorithm does find a cheap tour, then this cheap tour cannot contain any of the expensive edges. So on a more formal level, let's suppose this is the graph. This graph does not have a Hamiltonian cycle, obviously. Our algorithm B will add edges, will make it a complete graph. So this edge here will also be present in this one. But the edges it has added will become expensive, prohibitively expensive, indicated by red here. And prohibitively expensive means cost n times c for this hypothetical constant. Now, if the original graph does contain a Hamiltonian cycle, then so does the modified graph, but actually the modified graph will contain a Hamiltonian cycle, a travel-telling salesman tour, which is kind of cheap, namely it will cost at most n. Why is that so? Well, because the Hamiltonian cycle of the original graph only uses edges present there. It uses precisely n edges because n is the number of vertices, right? And these edges that are already present cost only $1 each, right? So that means n edges, the n edges of the original Hamiltonian cycle will incur total cost n. That's a kind of cheap traveling salesperson tour in this modified graph, provided that the original graph has a Hamiltonian cycle. Whereas if the, and of course that means that an approximation algorithm will find a tour, traveling salesperson tour with total weight at most n times c, because c is the approximation ratio, right? So whenever there exists a traveling salesperson tour of total cost at most n, then the one proposed by the approximation algorithm will have cost at most n times c, right? That's the first case. When the original graph has a Hamiltonian cycle, then the approximation algorithm will return a traveling salesperson tour of total cost at most n times c. In the second case, when the original graph does not have a Hamiltonian cycle, then any traveling salesperson tour is a Hamiltonian cycle, right? But the original graph does not have Hamiltonian cycles, so that means that any traveling salesperson tour will have to use at least one of the additional edges we have introduced in the algorithm B, and the algorithm B has made these edges very expensive, so that any traveling salesperson tour in this case will need to use at least one of the expensive edges, and therefore incur total weight at greater than n times c, because it course, must use also other edges. So that we have kind of this dichotomy of the original decision problems. Yes, it has a Hamiltonian cycle. No, it has no Hamiltonian cycle. This is now translated into a dichotomy on the approximative weights of the path returned by the approximation algorithm. In the first case, the traveling salesperson to return will have weight at most n times c. In the second case, the Hamiltonian, the traveling salesperson tour will have a total cost strictly larger than n times c, so that from the total cost of the approximate traveling salesperson tour, one can recover, one can deduce back which of the two cases was originally the original graph in. And this is precisely the decision problem, the Hamiltonian cycle decision problem. So put differently, using a hypothetical approximation algorithm, polynomial time algorithm with factor c, we can kind of convert that into an algorithm which decides the Hamiltonian cycle problem also in polynomial time, which we know is impossible unless p equals np. So that means that the non-metric general traveling salesperson problem cannot be approximated up to any constant factor c. And now why is that here with the non-metric? To this end, observe that the edge weights we have our algorithm creates here completely disregard any triangle or other inequality, right? So the new edges it creates could be very expensive. So let's, like for instance, going from here to here will be very expensive. Going all this way, this detour will only cost 3 edges, right? So this will cost n times c, and this will only cost 3 because it uses edges that are already present. So here we have already a violation of the triangle inequality. Taking a tour here is actually cheaper than taking the direct edge. So it's really the triangle inequality that makes the difference between admitting polynomial time approximation algorithm or not admitting polynomial time algorithm approximation algorithm provably. So this is what science and computer science is about. So to summarize, this is the end of chapter 8 on approximation algorithms. We've discussed the metric traveling salesperson problem, where we have triangle inequality. We have seen Christofides algorithm, which runs in polynomial time, although traveling salesperson problem is NP complete. And we've seen that it achieves a guaranteed approximation ratio of 2. So that's the difference between an approximation algorithm and a heuristic. Then we've considered the knapsack problem. We've considered as a maximization problem. First, we've divided an exact algorithm for that problem, a strongly polynomial time algorithm based on the dynamic programming paradigm. And then we have turned that algorithm into an approximation algorithm, namely by rounding the values of the packets. Since the values of the packets affect the running time, rounding them increases the performance, reduces the running time, but it also affects the value. And our analysis says that we can round in a suitable way so that both the running time still remains polynomial and the values, the approximations, will be at most 1 minus epsilon for any given epsilon, but as epsilon tends to 0, as the quality of the approximation increases, as the approximation ratio tends to 1, the running time of that algorithm also increases, but it doesn't increase too much. It increases only polynomially in 1 over epsilon, but not exponentially in 1 over epsilon. And approximation algorithms of this type, family of approximation algorithms of this type, are called fully polynomial time approximation schemes. And finally, we've seen that some some optimization problems cannot be approximated up to any constant factor unless p is equal to np, namely the non-metric traveling salesperson problem cannot be approximated up to any constant. So that's all for chapter 8.